Hi guys, welcome to our new episode. In this one, we are going to talk about some specific examples, specific utility functions, and try to understand how their indifference curves look like and how we can calculate their marginal rate of substitutions. All right, so our first example, these are highly common utility functions that we use in microeconomic theory. It's Cobb-Douglas utility function, and its functional form is something like this: x to the power alpha, y to the power beta, where alpha and beta are some number in between 0, 1. Okay, usually alpha and beta are sum up to 1. Okay, so the Cobb-Douglas utility function, it's sort of, I strongly recommend you to draw those indifference curves by yourself by picking up some points, all right? And so, for example, if alpha and beta are just 1, all right, this is just x times y, so the graph is going to be easier. But if it is alpha, say 1/3, beta is 2/5, well then you will need a calculator to draw it, or you can use some mathematical applications to draw it. But well, in fact, actually, for the indifference curves you need to. So a generic indifference curve of Cobb-Douglas utility functions will look like these. All right, and calculating marginal rate of substitution is relatively easy because the marginal utility of x, or there's no minus, del u over del x is just simple, right? It's alpha times x to the power alpha minus 1 times y to the power beta. And the marginal utility with respect to y is, del u del y, which is equal to beta times x to the power alpha y to the power beta minus 1. So therefore, the marginal rate of substitution is equal to del minus del u del x divided by del u del y, all right? And then that's equal to minus alpha x to the power alpha minus 1 y to the power beta divided by beta x to the power alpha y to the power beta minus 1. So if you do the math, right, this is this alpha minus 1, send it to here. So it's going to be x to the power alpha times x to the power minus alpha plus 1. So those alphas will cancel out. So I'm going to have just x only here. And here I need to send this up so that I will have only y here. So that means that's equal to minus alpha y divided by beta x. All right, so as you can see, the marginal rate of substitution, meaning how much additional y you need if you want to give up some of your x, is going to depend on your initial point of x and y. All right, so if you're here, well, your marginal rate of substitution is different. For example, when y and x are equal, well, then it's going to be minus alpha over beta, the marginal rate of substitution. But the minus sign basically means if you're giving up one good, you have to, if you want to get one good, if you want to get additional of one good, you have to give up the other. That's why we have this minus, because minus means the slope is decreasing, right? I mean, it's a downward sloping, but if we are somewhere here, for example, the marginal rate of substitution is different as well. All right, so this is what a Cobb-Douglas utility function and its indifference curve will look like. Well, what is next? Well, the next is what we call perfect substitute. We also use this utility function a lot, and unfortunately it gives a lot of trouble to our students, mainly because these utility functions are not differentiable. They are differentiable, but perfect substitutes. The standard optimization problems like Lagrangian or Lagrangian is not going to work in perfect substitute examples. So the utility function is of this form. alpha times x plus beta times y, where alpha and beta are just some positive real number. All right, this time they don't have to be between 0 and 1 interval. So we call this perfect substitute. Well, why is that so? I mean, I'm not going to go into the details because I know you guys already have seen those type of utility functions in intermediate micro or in principles. I mean, the introductory microeconomics courses. That we call these two goods are perfectly substitutable because consider the simplest environment where alpha and beta are equal to 1. So it's x plus y basically. So if you give up 1 unit of x, instead you need to substitute it by 1 unit, all right? As simple as this. So there's a one-to-one relationship between x and y. And here, there is a relationship between x and y is alpha over beta. So the marginal rate of substitution, if you calculate this, it's minus the partial derivative with respect to x, which is just alpha, and the partial derivative with respect to y is just beta. So alpha over beta and the marginal rate of substitution is constant. So that means if I have x versus y graph, the indifference curve is going to look something like this. All right, so this is one indifference curve, this is another indifference curve, and then this is another indifference curve. As simple as this. All right. So the next one is perfect complements. Perfect complements. Oh, by the way, just to mention, the standard examples for perfect substitutes are like, the coffee and tea are substitutes, perfect substitutes for many people. If you don't have tea, I can get some coffee, etc. Or sugar, sweetener, for example, perfect substitutes. And the perfect complements is like you cannot use one good without the other. Sort of a standard example is like, 4-wheel for a car. You need 4 of them to be able to use the car. So therefore, the fourth one is a perfect substitute for the other 3, in a sense. All right. Or a gasoline is a perfect substitute for car because you can't run your car without a gasoline. So a standard utility function is something like this: the minimum of x, y. All right. But sort of the more general form. Let's make it minimum of alpha x beta y. All right, something like this. By the way, I sometimes use the following notation instead: alpha x beta y. All right. Well, I mean, as you wish. To me, this is better. But either way, I am okay. So, well, what does that mean? That means if you look at the simplest environment, minimum x, y, right? So your utility level is going to be fixed as long as the minimum condition is not satisfied. So here's the indifference curve will look like. So I'm going to draw this. So how do we draw an indifference curve? Let's fix this to some constant number. Well, I just randomly pick one constant, and let's say it is 2. All right. So what are the values of x and y's where the minimum of these two are? Look, this is minimum of x or y. So whichever is the min, that's going to be my function, the outcome. So if you want to be more formal about it, it's minimum x, y. It's something like this. So the value is going to be x if x is less than y, and it's going to be y if y is less than or equal to x. All right. So that's it. So the minimum value is either x or y. It can't be something else, I mean. And it is x if this is true, and it is y otherwise. That's as simple as this. So the minimum of x, y is equal to 2. So when this is possible, for example, when x is 2, y is 2, well, then the utility is going to be 2. All right, so that's on my indifference curve. What else? So let's keep x being 2 and increase y. So y is 10, for example, 2 comma 10. So which one is smaller? Well, clearly 2, right? So therefore, my utility level is still 2. So as long as my y is greater than 10, all these points, I mean, will be on the same indifference curve. But the y's in this region, right, y, for example, 1, the minimum of 2 to 1 is not going to be 2 any longer because y is now less than x. So therefore, I cannot go below 2. So y has to be greater than or equal to 2. Okay, now I fix y as being 2 and increase x. So if x is increasing, doesn't matter because x is greater than y, which is 2, my utility is still 2. All right? So therefore, my indifference curve is going to have this L shape. All right? And they're going to move in this direction. Well, by the way, when we say they're going to move in this direction, all these functions are increasing functions. So as we move in the northeast direction, it means higher utility. So if I am drawing this indifference curve for utility level 2, this must be indifference curve for utility level 3, this must be indifference curve for utility level, I don't know, 5. So that means higher utility as we move in this direction, and therefore as we move in the towards the origin 0, 0, that means less and less utility. All right, so one question is, what is the marginal rate of substitution, right? What is the marginal rate of substitution here? Well, what is the derivative of this min function? So that's confusing. I mean, this is not a differentiable function. It's a continuous function, but it's kinked, so it's not differentiable. Therefore, what am I going to do? Well, I mean, it's undefined, basically. Well, why is that so? Well, because in this region, for example, all right, in this region of my indifference curve, the slope is what? I mean, it's completely perpendicular, and the tangency of this perpendicular line is infinite. It's not well defined. I mean, it's undefined. Well, what about here on this horizontal axis? So here, at any point, the marginal rate of substitution is 0 because the slope of this part is well, the tangential line is just tangent to the x-axis, so therefore its slope is 0. So therefore and at this point, by the way, because this function is not differentiable, the tangential line slope is undefined because this is a tangent line, this is a tangent line, this is a tangent line. You see what I mean? I mean, at this kink point, any straight line that is touching to this point 2, 2 is a tangential line. So therefore, the slope, any slope is going to be fine at that point. And so that's kind of why this function is not differentiable. So therefore, the marginal utilities are not differentiable. Marginal rate of substitution is not defined. So the marginal rate of substitution is not possible to calculate. It's possible. All right. So the next example is what we call the CES utility. It's also widely used utility function, especially in macro theory. And and its functional form is something like this. U of xy is equal to x to the power delta plus y to the power delta to the power 1 over delta. All right? That's it. So, the delta is just any number, all right? It's just a real number. Delta is just a real number. Well, I mean, here, if you... I mean, obviously, we prefer to have it like a positive real number, obviously, right? And non-negative maybe. But you would be fine if it is negative as well. Then the function is not going to be an increasing function. All right, so here, a very specific condition. When delta is equal to 1, for example, this term becomes u of xy equals x plus y, right? It's then perfect substitute. All right. So sometimes working on this is not so easy. So what we do, we look at its its monotonic transformation. All right. So it's monotonic transformation. How do we transform it? Well, we define this new utility function u star by basically multiplying my utility function with delta and then dividing it by delta. All right? And again, here I assume that, delta is a positive real number. Otherwise, it wouldn't be increasing transformation. All right? So here, right, this is an increasing function of u. I just multiply this delta, all right, and then divide it by delta. So my new utility function is basically this x to the power delta divided by delta plus x to the power, y to the power delta divided by delta. Well, why do I want to do a transformation like this? Well, simple, because here is the reason. If u represents some preference relation, then u star also represents this preference relation. And the other way is also true, right? This is an if and only if statement. So therefore, more formally, u represents this preference relation if and only if u star represents this preference relation, all right? So basically, these are two different utility functions which represent exactly the same behavior, all right? So that means if you are, for example, solving a maximization problem with this utility function, the maximum allocation for this consumer will be exactly the same if you do the maximization problem instead of this utility function, all right? Because they are an increasing transformation or monotonic transformation of one another, all right? So that's kind of an important trick. As I said, whenever you find the functional form problematic, you can always make a transformation of this form. All right. So before I sort of close this episode, I like to talk about what we call homothetic preferences. Oops. So it's just a special name we give to a certain group of preferences, and the homothetic preferences has to satisfy the following condition: the marginal rate of substitution is same for all indifference curves. MRS is same at all, that's better, at all points on the same array. Well, what does that mean? That means if I draw an indifference curve of a utility function, and this is another higher indifference curve, and an array is something like this. It doesn't have to be a 45-degree line, but it's a straight line starting from 0 and goes to infinity. All right. The marginal rate of substitution, I mean the slope here is going to be exactly the same as here, and the slope here is going to be exactly the same here. So the marginal rate of substitution here and here are not the same, but the marginal rate of substitution at this point is equal to at this point. All right. Or put it differently, this is what? This is some line y equals k times x, right? So array basically means that, k is, this is x. K is some positive real number. So y equals k times x is just, a straight line starting from 0. So along this line, the marginal rate of substitution is fixed. And if you remember, if you remember the Cobb-Douglas example, in our Cobb-Douglas example, I had the marginal rate of substitution equals minus, I forgot what was, alpha divided by beta y over x, right? So therefore, the marginal rate of substitution on a line, on an array, is nothing but alpha beta times kx divided by x. So the x's will cancel. So it's alpha divided beta times k. All right. So if you increase k, you're going to get sort of a steeper straight line. And so the marginal rate of substitution, the absolute value is going to increase. All right. But not all preferences are homothetic. And in fact, one very famous utility function that does not that is not homothetic is basically what we call the utility function xy equals, let's be more specific, x plus ln y, for example. All right. So in this utility function, the indifference curves are not going to be have this nice shape, meaning their MRSs will not be fixed along an array. And the marginal rate of substitution, if you calculate this, it's minus the marginal utility with respect to x is just 1, and the marginal utility with respect to y is the derivative of ln y, which is just 1 over y, so it's minus y only. So the marginal rate of substitution depends only on the y good. All right. Okay, so one final thing before we conclude is the transitivity of preferences and indifference curves. So if you remember, I keep drawing the indifference curves, the higher indifference curves, somewhat parallel to each other. But is it really always the case? I mean, can I have a preference relation with an indifference curve like this, and then another indifference curve like this? Is it possible? Meaning, two indifference curves intersect with one another at some point. Is it possible? Well, this is not possible if preferences satisfies monotonicity and transitivity. All right? Why so? Let's suppose this is true. Okay? Meaning, let's suppose two indifference curves can intersect at some point. Let's call this point point A. All right? I am going to pick random, not completely random though, two more points. I'm going to call this B, and I'm going to call this C. Okay? So now I am going to make some observations about those points A, B, and C. What do I know about point A and B? Well, they both are on the same indifference curve. So therefore, this agent must be indifferent between A and B. Or equivalently saying, the utility in both A and B are the same. Very well. What else? Well, C and A are also on the same indifference curve. That means the agent must be indifferent between C and A. So that means the utility of A is equal to utility of C. Sorry, this should be utility of B. Right? Utility of A is obviously equal to utility of A. Stupid mistakes. Well, then, what else do I know? Well, I mean, look, these are real numbers, right? If real number UA equals UB and UA is equal to UC, therefore, by logical deduction, UB has to be equal to UC. What does that mean? That means B and C must be indifferent, right? Oh, yeah, okay. But the thing is, so this is by transitivity. Don't forget that, by transitivity. Because of the transitivity assumption, all right? Again, because of the transitivity assumption, I can represent that's very important. All right, so this is a preference relation. It's transitive, it's complete, it's reflexive. So therefore, it can be represented by a utility function. And because of this, this has to hold. All right? But that comes from the fact that this is actually a transitive binary relation. All right. Well, what else? Remember, I also said if your preferences are monotonic or increasing and transitive, well, clearly this can't happen. So how do I know that? Well, look, C is a vector which gives me this much x, this much y. but B is giving me more X and more Y. So if your preferences are monotonic, or for simplicity increasing, that means you should actually prefer B to A, or B should be strictly better than A, all right? You're not even indifferent, but you should strictly prefer B to A because, again, B gives more, therefore it should be preferred. But the thing is, we just sort of concluded that B and C must be indifferent. I mean, the agent must be indifferent between these two, therefore has to give the same utility level. But then, thanks to monotonic preferences, by the way, for those who do not know this lingo, monotonicity, a function is increasing or could be increasing or decreasing, increasing everywhere, decreasing everywhere. In this case, we call such functions monotonic. I said, an increasing function could be monotonic, a decreasing function can also be monotonic. Monotonicity is sort of a more general name. All right, so even though the preferences are decreasing, all right, monotonic but decreasing, doesn't have to be increasing. Well, this time it's going to be UB less than UA, but let's suppose it's an increasing preferences or utility function. So therefore, we just show also, thanks to monotonicity of preferences, B must be better than A, or the utility of B must be higher than A. Well, this is clearly a contradiction, right? Because these two arguments, these two and these two cannot be true at the same time, because this is negation of this. The opposite of, well, not opposite, but sort of, they both cannot be true. So therefore, a transitive and monotonic preferences, or preferences are transitive by definition, but increasing monotonic preferences and their indifference curves cannot cross one another, or never. It's impossible. So therefore, they have to be sort of parallel to one another on this space. And don't forget, there's not just one or two indifference curves. As you change the constant u of xy equals c, as you change this constant, you're going to get another higher or lower indifference curve. And so c is just a real number, right? And so therefore that means there are infinitely many indifference curves basically floating on our space, and they never cross one another. So that's the property of such preferences or utility functions. Hope that was clear.